Example 9 gives us another free response question here. We've got ourselves a graph, and it says a car is traveling on a straight road with a velocity of 55 feet per second at time t equals 0. For the closed interval from 0 to 18 seconds, the car's acceleration, a of t in feet per second squared, is a piecewise linear function defined by the graph above. Nice. On the time interval from 0 to 18, what is the car's absolute maximum velocity, in feet per second, and at what time does it occur? Justify your answer. So, remind me, if you will, if you're looking for an absolute maximum on a closed interval, what is the test that you need to perform? Could it be possibly the closed interval test? Well, you would be right. Sometimes known as the candidate's test. Okay, well, up until this point, whenever we used the closed interval test, we had some sort of equation that we could take the derivative of in order to find critical values, made a table of values, and then checked it against the endpoints, the critical values, to see which one was the biggest or which one was the smallest. Okay, so we're going to have to apply that now to just having a graph. Okay, so notice that I want absolute maximum velocity. Okay, I want abs max velos. How do you spell that word? I think that's right. Which means that you need a velocity equation that you can take the derivative of, right? So if you have the velocity equation, you take its derivative, v prime of t, you'd set it equal to 0 in order to find your critical numbers, right? I'm going to do all of those things, but just using the graph that's right up here. The graph is of a of t. So what do you have to do to a of t to get a velocity equation? You have to take its antiderivative. And it would look like this. I would take a of t, or actually the definite integral, from, what time does this thing start? Time equals 0, yes. From 0, don't put 18 up here, because if you go from 0 to 18, you're just getting a number. You're not getting a function that we can plug different numbers in. So I'm going to put up here a t, because we want v of t, and then a of, don't put in a t here. Maybe I'll make this one an x, dx. Or I could have switched these two things, right? As long as it's not the same variable. Okay, so now let's apply the fundamental theorem of calculus to this. I would need an antiderivative of a of x. I'm pretty sure that's v of x. And then we would evaluate that from 0 to t. So applying the fundamental theorem of calculus, that's going to give us v of t, which is what we're looking for as an equation, and then minus v of 0. They gave us v of 0, and v of 0 is right here. It's 55 feet per second, so that's our initial. So it's like 0, 55 we're going to use. So I'll plug a 55 in here, and then just add it to the other side of the equation in order to get a velocity equation that we can take the derivative of. So v of t is equal to our initial position of 55 plus a change in position. I'm saying position, but it's actually velocity, right? An initial velocity plus a change in velocity from 0 to t of a of x dx. All right, here's my equation. This is the thing that we needed right here in order to find the derivative of, to find our critical numbers. So we can actually apply the closed interval test to this thing. Okay, so let's find its derivative. So v prime of t is equal to, what is the derivative of 55? It's 0. I'm not going to write it down. Plus, how do I take the derivative of an equation based on a definite integral? I think that's the other fundamental theorem of calculus. Remember, they cancel each other out with just a change in variable. This t just goes straight up in here. That is equal to, why did I put this plus sign? I don't even need it. It's just equal to a of t. Right? Of course it is. And that's the graph that we have. That's right up here. So, of course, doesn't that make sense? that this a of t is equal to v prime of t. Okay, and I needed that so that I can set this thing equal to 0 to find its critical numbers. So its critical numbers would be where a of t is equal to 0. And that happens at 6 and at 16. T equals 6 and 16 seconds. Okay, so then what I need to do for that closed interval test is make myself a little table of values, which should look like this. There's no intervals that happen here. It's just table of values where I have t versus our v of t. I'm going to make this rather large because we're going to need some room to write. All right, so what are the candidates which go over here? Your candidates are, of course, your critical numbers, which we listed here, in addition to the two endpoints. Remember, we got to test it against the endpoints. The endpoints would be 0 and then 18. Hopefully that's enough room here. And then we also have 6 and 16 as our two critical numbers. All right, the first part is real easy. I don't even have to use the equation. They gave it to us. It's 55 feet per second. Okay, we're going to compare the other ones to that. Okay, so to get 6, it would go like this. My initial is 55 plus the change from 0 to 6 of v prime of t, which I can just write as a of t. Actually, it was a of x, wasn't it? dx. Okay, just like we did in the previous example, this part right here we're going to get as area. So this is area. Area underneath that graph. So if I come back over here from 0 to 6, let's take a look. From 0 to 6, I have myself, it looks like a trapezoid. You can break that up as a rectangle and a triangle if you want to, or just a trapezoid and find its area. I'm going to do it as a trapezoid. So our area here, I'm writing with a highlighter, awesome. Area should be equal to, our two bases are going to be the top and the bottom right here because those are the parallel ones. This is 6 up here and this is 2. 1/2 6 plus 2 times my height of 15 here. So that's 8. Half of 8 is 4. 4 times 15 is 40. 20 is 60. That is equal to, so 60. 55 plus 60 gives us 115 feet per second. I think, right? And then let's keep going. So obviously we have 6 is winning, but here, let's think about this for a second. If I start at 55 feet per second whenever I basically, let's say at time t equals 0, then since my derivative is positive, then that means that as far as the velocity equation is concerned, it's going to increase, right? My velocity is increasing till I get here. I know this looks like it's decreasing because the acceleration is, then it's increasing by less and less and less because it's approaching the x-axis right there, or the t-axis, I should say, right? So this one right here so far is a maximum, right? And I would have known that that was at least a relative maximum. And then this point over here is going to be a minimum. And as a matter of fact, you could point that out, that this is a minimum because your acceleration changes from negative to positive here is a minimum. So that one can be eliminated. I'm going to go ahead and include it though, since it was one of my critical values in the desire of being thorough here. So this is 55 plus definite integral from 0 to 16 of a of x dx. All right, I already have 55 plus the 60 that we had before from this one, and then we're going to take away the area from 6 to 16. So now we have yet another trapezoid. Let's make this one red because it's below the x-axis, and that red and green, they're really going to look good together. Color, 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 color. And voila. All right, let's see what we have here for this one. Once again, using our trapezoid area formula, we have area is equal to a half of our two bases. Let's see, this one is 4 here because I'm going from 14 to 10. So 4 plus, and then this one's going from 16 to 6, so that's a 10. And then our height is, oh, it's also a 15. So I got 14. Half of 14 is 7, so I need to do some arithmetic over here. So I have 15 times 7. 35, 3, 105. Minus 105. So we already knew that that was 115 minus 105 gives me a total of 10 feet per second. Okay, there we go. So obviously that's looking like the minimum. And I know that that one's going to be a minimum simply because what happens to the derivative after that is, now it's positive. So the acceleration is now positive, which means your velocity is increasing at this particular point. Right? Okay. All right. But is it going to increase from 10 to enough to get back up to this 115? Heck no. It's a tiny little triangle that I have to add to it. So I have 55 plus the definite integral from 0 to 16 of a of x dx is equal to all of the stuff that we had before, which is 10. I'm going to redo it, but then plus this little extra change that we have for this triangle, going back to green. It's above the x-axis, so this part that's right there, from 16 to 18. All right, we will use another area formula here. So its area is 1/2. The base length looks like it's just a 2. Height back to being 15. So the 2 and the half cancel out. I just get 15 for a total of 25 feet per second. Try that again. There we go. And then the only thing that remains is for us to actually write up our answer here. The justification for an absolute maximum is the work that you do, right? You have found the critical numbers, you found the candidates, you found the y values or the velocity values at each of those, and you just point out what's the maximum. So the absolute maximum volume velocity of 115 feet per second occurs at t equals 6 seconds. There you go. So I just made a final conclusion, make it look real pretty. Don't just rely upon like this as being your final answer. Actually write the thing out. And once again, your justification is all the work that you just did.